Yes, doesn't it?
Oh, yeah.
Tell her I said, hey, enjoy your, did you say junior year or sophomore?
Sophomore.
Sophomore. Okay, that's an exciting year.
Yeah,
Tell her I'm thinking about her.
I will. Thank you.
Can you hear this? There we go. That's a little, move this away.
Yeah, we got some more folks now.
How's that?
Beastly, Roger. Hi, guys.
Well, I'm going to get started with our meeting. Welcome, everybody, online and in the room. Welcome to our November meeting of the astronomy section, Rochester Academy of Science. My name is Mark Minerich. I'll show you my face real quick. Hi, everybody. Currently a president. R.I.T asked us to wear a mask, so let's keep our masks on, keep ourselves safe. Thanks for coming, everyone. Welcome to our November meeting. I see we've got a number of people online. I think we might have some guests as well. I see some names here that look like they might be from the Mohawk Valley Astronomical Society. So welcome to you guys.
What's happening to these men and how they're being treated. And I do believe.
Don't be offended if I mute you. All right. Welcome. Can you guys see my presentation if you're online? Okay, excellent. All right. Let me scroll through here. Get over somewhere. Okay. All right, so is there anybody, this is the first astronomy section meeting you've ever been to? Raise your hand. This is the first meeting you've ever been to. No, he's been here before. Anybody new in the chat this first time here? It's all regular people. Well, welcome everybody. Glad you guys are here. Let me ask if anybody has done any observing in the last month or so that want to share with the group. Has it been too cold to do observing, or too cloudy? Too cloudy. Well, you see the pictures on the slide. There's two images, so two of us did some observing. One of them was Kevin Lyons, who's been imaging Jupiter and Saturn. He did a really nice image of Saturn. I shared that on the slide with us today. And then I went up to the big dome in when was it? Sometime in October. And I moved it back from the Hyperstar to the natural F11 mode. So it was an F1.9, so a very fast telescope to a very slow telescope. Basically, so we could take some planetary images and get some nice deep sky stuff as well. And so while I had that in there, I want to make sure that I collimated everything correctly. So I did an imaging session on Jupiter. This is about a 3-minute exposure, video exposure of Jupiter. And I stacked that up took that in a software called called Auto Stackered. And then I took that and I put it into Registax, and I'm able to bring out those bands and stuff using Registax. And I accidentally got a moon next to Jupiter when I was doing all that because of the size of what I was developing. So I think that's Io right next to Jupiter. Oh, that's all. That's the extent of my observing. We do have some observing coming up, and I'll show you. Oh, I did do one more thing, and I'll talk about that when we get further into tonight's meeting. That's right here. So I hosted the cast and crew of Silent Sky on October 18th. It was a Saturday, and if you remember that day, it was really nice. It was good. It was really nice. It was really cloudy and rainy all day. It was clearing up at the end of the day, and we actually had a window that it cleared up. We actually were able to look at several objects that evening. We looked at Jupiter, Saturn. What else did we see? We looked at a couple star clusters. So I was able to give the cast and crew of Silent Sky a little bit of a sky tour for that evening, and they thoroughly enjoyed it. Two young boys, sons of Jill Rittenhouse, who plays Henrietta Leavitt in Silent Sky, got to open up the roll off, got to close the roll off, and everybody got to look at the sky. So it was a fun night, even though it was really short because the nature of the night. But that's a picture of the crew, cast and crew that showed up there. There's Jackie in the back of the room now. So Jackie was there. She's smiling in the back row there with her Eclipse shirt on. So it was fun having the cast and crew there, which will bring us to another thing down the line of when that is. So here are some of the upcoming events that we have going on. We've got Member Observing tomorrow night, and it looks to be clear tomorrow night, but it also looks to be about 38 degrees. So if you want to observe, certainly going to be a nice night to do it, but it will be very cold. So, and if you're standing still looking through a telescope, it feels even colder than if you're moving around. So I highly recommend very heavy clothing if you're going to go out and observe. I plan to be there at about 7 or so, and I'll open up. Am I getting an echo? And I'll open up the Ferris Center. I'll make sure that there's plenty of water and Keurig cups to make hot coffee and chocolate, so we can enjoy a little bit there. And then on Sunday, we have an open house from 12 to 3. Roger McDonald will open up the Ferris Center on Sunday for people to take a look at the site. If you haven't seen the site, you want a tour, you want to learn how to operate stuff, or you want to help Roger with some of his projects. He's always got projects. Come out on Sunday from noon to 3 to an open house. And then we have our regular board meeting. We're meeting at the U of R in the chart room up in the Bausch and Lomb building. It's room 480 on Wednesday next week at from 7 to 9 for our board meeting. Any members welcome to join us for the board meeting. Certainly want input from anybody that wants to come and give it. So if you want to join us from 7 to 9 at the U of R on next Wednesday. Yes. Oh, yes, it is Sunday. It says Saturday, but it is the 7th and it's Sunday. So thanks, Peter. Yeah, 12. It's a long open house. Yeah, it's right after observing. Poor Roger. The following weekend. Now, this following weekend we have Silent Sky. It has the Blackfriars Theater all weekend. We have a reserved block of seats on Saturday the 2nd. If you want one of those seats, call Blackfriars and you can get a 15% off ticket, a $31 ticket for Silent Sky, which is the story of Henrietta Leavitt, who is, if you know Henrietta Leavitt's about, she is one of the computers that worked at Harvard University for an astronomer there. And she's responsible for figuring out that variable stars blinked at a very steady rate. And by using that information, we were able to tell how far away stars were. So it gave us the ability to figure out distances much, much farther away than we've ever been able to figure out before that time. So it's an incredible discovery that she was responsible for. And this is a fictionalized story, so there's a little more to it than just that, but that's the crux of what Henrietta Leavitt did astronomically. Sounds like it's a really good show. The reviews have been phenomenal. I showed up for a salon afterwards of the Sunday show last week. I got all kinds of astronomical questions, so it was fun to help them out with that. But I highly recommend that. You want to come to the show with a bunch of us. I think there's at least 10 of us that have reserved seats for the 2 o'clock show on Saturday the 12th. The 13th, excuse me, Saturday the 13th, but there's shows on the 13th as well. Look on the website. You can go to any show you want, but there will be a bunch of us at the show on the 13th. Anything I missed, Jackie?
No, that's it. I'll be there every night.
She'll be there. Jackie Emagon is the stage manager for Silent Sky, so she's intimately involved with everything that's going on there. All right, that's that. I have another event coming up that same day. I'm going to rush back from Silent Sky, and I have a STEM team, an urban suburban STEM team led by a guy by the name of Kelvin Knight. And every year I've gotten together with Kelvin and a number of kids from the city to come out to our site, and they give them a little astronomy presentation, and then they get to use the telescopes. They're coming out next Saturday, the 12th, at about 5:30. And we'll get, pardon me? Thank you, the 13th. I'm doing this off the top of my head, thank you. Saturday the 13th, but the same day that we're doing the Silent Sky. Yeah, I got to put my glasses on. Here we go. Now I can see it. All right. I'm glad to have any help that if anybody wants to come out, come see me after the meeting. Glad to have any help out there with these kids. We'll probably roll off the 20-inch job and look at some stuff if the skies are clear. Right now, it doesn't look really good for that Saturday night. All right. A big event. We didn't have a Rochester Star Fest this year, but I'm determined that we're going to have a holiday extravaganza at the Strasbourg Planetarium. And so you got my note earlier this week. We are going to be able to have an event there. The RMSC will let us have 100 people in there as long as we're masked and vaccinated. It's to be determined whether we're going to require proof of vaccination at the site. That will come in a further email. We'll make that determination shortly. But there's a lot that's going to happen that evening. We're going to try to serve snacks, which will be served, not going to be your traditional potluck where people bring in stuff from home. One of the rules of the planetarium is it has to be brought in food and served. We don't want any possibility of any contamination coming in from home into the planetarium. So we'll have it catered. It'll all come from one source or a reliable sources, and then served safely. And you can take your masks off while you're eating or drinking. And we'll do that for an hour from 6:30 to about 7:30. Then we'll go into the Star Theater, all 100 of us, and we'll have our regular meeting, much like we're having right now. This lasts about 20 minutes typically. Our regular meeting is about 20 minutes, maybe a half an hour, which will be followed by our feature talk, which is Dan Schneiderman, who is the Eclipse Planning Coordinator for the Rochester Museum and Science Center. And it's a bigger job than you might think because they're really trying to plan the 2024 eclipse for the region. It's a big deal. It's going to be affecting multiple counties, multiple institutions, traffic, state police, a whole bunch of things are going to happen in order to pull off hosting the 2024 eclipse. And so we'll have Dan talk a little bit about what's going on with the planning for that and how we will be involved with that as well, or can be involved with that as well. So it should be an interesting talk. It's only 3 years away, so not even. It's only 2.5 years away, 2 years and a few months actually. So it's coming up very, very quickly. And then we'll have a member images section, which I'll explain how that's going to work in a moment. That'll be about half an hour, and then we'll do a presentation of Black Holes Revealed, which has, how many people have seen Black Holes Revealed? Nobody seen it? Anybody online seen it at the planetarium? Really good show. It'll answer a lot of questions about black holes. It also fixes a lot of misconceptions about black holes too. So it's an interesting show. And at the end of that, typically we take you on a tour of the night sky for that night. But what we'll do is we'll ask Steve to give us a highlight tour of what's in astronomy for 2022 afterwards. I thought that'd be a fun thing to do. But it's a busy night. It'll be from 6:30 to 10, I'm saying 10:15. It could be a little late. So, but it is a Saturday night. So live large, take a nap in the afternoon. Friday night. Friday night.
You need an administrative
Friday the
assistant.
4th. Friday the 3rd. Friday the 3rd. I am way off on this tonight. Wow. So much for my proofreading, but it's Friday the 3rd. All right, any questions on the holiday extravaganza at the Strasbourg Planetarium besides the day? It is Friday, December 3rd. Excellent. All right. Then going into the rest of September events, we have our regular we'll have a regular observing and open house on Saturday and Sunday. Again, I use the same slide template, so it's a Saturday and Saturday, but Saturday and Sunday, and then our board meeting on Wednesday, just like we have it previous month. Coming up, here's the next few months after September. We don't have a planned speaker for January yet, but Dave's working on it.
We got one.
Dave's got one. Well, who is it, David?
Husband is going to bring in 3 of his grad students.
Who is?
Mike Richmond is going to bring in 3 of his grad students.
Mike Richmond's going to bring in 3 of his grad students,
And those grad students are going to be presenting their research in astronomy.
and these grad students will be presenting their research in astronomy for those of you online. So that's okay. Then in February, this should be an interesting talk by Mika Nakajima, who works with Anna Quillen or Alice Quillen and in planetary astronomy. So it should be interesting. She's also a geologist. So we're going to kind of get a combination of what's going on there with from Mika. And then in March, we'll have Judy Pfeiffer, Professor Emeritus from U of R. And we don't have a title for her talk yet, but Judy's going to come talk to us. She hasn't talked to us in a long time, so we'll get forward to having Judy back to talk to us. Judy actually has an asteroid named after her. Do you guys know that? And we could probably image it sometime in like May. I think it's a good time to do that. So it was a project I was going to try to do, but never got around to it. So that's what's coming up in the next few months. And I'm very sorry about all my days being all messed up.
Hey, Mark,
Yes, Michael.
the December Christmas party is on December 3rd, not December 5th.
Yes, you are correct, Michael. It's December 3rd. Thank you. Yes, thank you. I put the Ferris Center protocols on a slide. They haven't changed. So it's pretty straightforward what we do at the site. If you're going to be in enclosed spaces, please wear a mask just to protect yourself. You must sign in so we know who's been there. If there's a chance that there was a spread of the COVID virus, we need to know who was there at the same time. So during these open houses or any other event that's at the site or the observing nights, we need to know who's there. So in the event that there is some kind of a spread, we know who's there. We can track people down, let them know they've been exposed or not. Bathrooms will be open for not much longer. The upstairs bathroom will probably be closed sometime before Thanksgiving, but the downstairs bathroom will be open for use at the site at that point. And just wash it, sanitize your hands. You guys have been through this for the last 18 months, so I'm not going to berate it. All right, is he here? He's in the back of the room. He's got his green ASRAS shirt on. In the back of the room is Tony Gollenbeck. You have not picked up your shirt yet. Tony is tired of dragging these across the 2 counties to get them here. So, and you know who you are. Go see Tony, get your shirt. Your last chance is going to be at the Christmas party. Then I'm going to tell Tony, just leave him at the Ferris Center. We'll figure it out from there. Thank you, Tony, for doing it, though. We love our ASRAS gear. You guys like your ASRAS gear? Yes, yes, yes. Nice to be able to represent. So, well, come see Tony for your gear if you haven't seen him yet. Finally, it is membership renewal time. We got a couple months left in the year, and we do have, if you are here today in this building, over here in a green shirt with a yellow sweater next to him is Craig Kaplan, our membership chair, and he will gladly take your money, your check, and your form, and you don't have to pay a processing fee. You can see him right here to renew your membership. And a first class stamp, yes. All these savings, if you can see Craig today, and Craig will also be at our meeting in December. We'll have a membership table set up while we do the snack time. We'll try to get Craig a snack before he takes all memberships there, but he will have a table set up to take your membership just during snack hours. So don't delay in getting Craig your membership renewal. This is the best value you can get for your buck. So think about what you get out of ASRAS, whether it's COVID time or not. We got all kinds of stuff going on. So sign up and re-sign up. Anything else, Craig?
No.
Awesome. Yep, if you need a form, he's got it. You don't need to delay. All right, with that, it's election night, and here is our slate. And if I could get some help up here, I have a ballot for everyone here. And for those of you online, I would ask that you look at the slate that you see on your screen. And if you like the slate, put a thumbs up. If you don't like the slate, Let me think of another reaction we can put on here. What a different reaction than a thumbs up. And we'll count your votes as well. So I'm going to ask Peter to hand these out. Here's a couple of pens. I have to take one too. Hang on. I got to write somebody in. No, I'm only kidding. All right. We are going to do our voting.
So Mark, the thumbs up don't stay on very long. So you ought to, you know, say we're going to do it now and then have everybody at once, okay?
So let's do the thumbs up right now. Awesome. Awesome. Okay.
Anyone else has pens? We're very short.
All right. We had a good showing online. After you've voted, just pass them all down to one side and we'll collect them. And Peter Blackwood will be the election that will count the ballots. And then we will count those up and give the results after a couple of minutes here. Let's see. I think that's it for us here.
So Mark, I think what happens is on the screen, you have to select reactions. Then you have to put a thumbs up. I didn't see anything come up for a vote. So I selected it and it showed up as a thumbs up on under the invite and under the participants. Is that correct?
Yes.
Okay, good.
Oh, we all just turned on our cameras.
Yeah, that'd be great if you guys want to collect them all. All right, while they're being collected, let me introduce our speaker for tonight. Segev BenZvi, did I pronounce your first name correctly? Of the University of Rochester. He's spoken to us before. I believe we talked about neutrinos and something in the south. Yes, that was kind of a very interesting talk. And without further ado, I'll bring Dr. BenZvi up and remove this. And I have your thing on here. What we'll do is we'll share that. Microphone. Yeah, this, you know what you're doing. You don't even need me.
I don't sit up there.
Let me stop sharing the other one then. Oh, I don't. I know we got to do. Hold on. This.
These are blank.
No, wait.
Present to the top.
Everyone online can see that? You guys see the presentation on their screens?
Yes.
Oh, it's all you.
Yes.
Yeah.
Thank you for the invitation to come here. I was here in, I want to say 2018, but it might have been 2017. And I spoke to you about the Ice Cube Neutrino Observatory, if you remember. I recognize some faces. It was a really fun experience for me. You guys asked a lot of very probing and penetrating questions. I imagine that'll happen tonight. what I'll do today, I'm going to talk about the other half of my research. So part of what I do is particle astrophysics, is the study of high energy radiation from outside the Earth's atmosphere. The other half of what I do is cosmology, the study of the origin and evolution of the universe. So that's what we'll talk about tonight, focusing on the Dark Energy Spectroscopic Instrument. Okay, so let's begin with a discussion of the basic assumptions of cosmology. What is the field about? What do we know about the universe now? And more importantly, why do we know it? So this might be a review for some of you, hopefully not for everybody. If it is, you guys can start motioning to me to hurry up and not dwell on points that you've already heard. So we'll talk about how we know what we know about the universe. Then I will focus in on a specific kind of measurement, the surveys of large-scale structure in the late cosmic time, recently formed structure in the universe. That's what we're going to be talking about tonight. And then I'll zero in finally on the Dark Energy Spectroscopic Instrument, which is a survey, a 5-year survey, about 30 million galaxies and quasars, out to a redshift of about 3. And it is more than 20 times larger than the previous redshift survey that's been done. So it's a massive expansion of our knowledge of the late universe. Okay, so let me explain the universe we live in. Most of you know that we live in an expanding universe. And on the largest scales, the most important interaction is gravitational. It's mass interacting with other mass and attracting it. But also some other things that I'll tell you about in a moment. So some evidence for this that you probably know about is the Hubble expansion of the universe. This is actually a plot from Hubble's paper in 1929, where he plotted the distances to nearby galaxies. He called them nebulae. They weren't called galaxies at the time. On the x-axis, and on the vertical axis, the velocity. Now, the way that he measured distance, we were talking about Henrietta Leavitt. Her work was important for establishing some of these distances. The way he measured velocity was that he looked at the color of the galaxies, specifically at the spectra. He found that the further away galaxies were, the more their wavelengths were shifted towards the red end of the spectrum, which is a Doppler effect. It indicates a recession, a movement away from Earth and in all directions. So the universe appeared to be expanding, and this was a major, major discovery. Another piece of evidence in support of the expansion of the universe, if you look back at much earlier cosmic times, in nearby galaxies, to essentially the edge of what we can observe, you see something like this. So this is not a visible radiation. This is actually microwave radiation, long wavelength radiation. And this isn't really what the microwave sky looks like. It's very processed. It has the foreground of the galaxy removed from it. This is actually the background radiation from a period in the early universe when it was very, very hot, much more dense. Essentially, the radiation as the universe is cooled. And this is evidence that at some time in distant cosmic history, the universe was much smaller, much hotter. And this is the radiation left over as it was cooling off. So that's another piece. This is called the cosmic microwave background radiation. Then more recently, only about 20 years ago, we get additional interesting evidence of the expansion of the universe, looking at different kinds of objects that can be used to measure distances. These are type 1a supernovae. So this is the explosion of white dwarf stars when they accumulate matter around themselves. And you can use that as a means of measuring distance on cosmological scales. So this is builds again on discoveries like Henrietta Leavitt. And what was discovered in 1999 was that the distances of these supernovae were not consistent with a universe that was expanding at a steady rate. The expansion is actually increasing in rate over time. So we have an accelerating expansion. And what is driving that accelerating expansion is unknown, called dark energy. And that's about all we know about it. We made up a name to give the phenomenon something, and we really can't tell much more about what it is. I'm going to tell you as much as we know, and then what we're trying to do to gain more knowledge. Okay, so here's a picture that I think many of you have seen before, a public image, a cartoon of the evolution of the universe put out by NASA. So the picture that we have, and I'll start justifying why we think this is the picture, is that initially, the universe started in a Big Bang. The exact conditions there are speculated on, but we think there was a very hot and dense plasma that then underwent a period of extremely rapid exponential expansion. That's called inflation. The evidence that we think inflation exists is that if you look in many different directions in the universe, they're so far apart, they're actually causally disconnected from each other. They look the same. The universe looks the same in all locations, in all directions, as far as we can tell. And we think inflation is responsible for that. Then, at the time, the universe, after inflation, was very, very smooth. There were no galaxies. There were no stars. There were very small, almost part per million fluctuations in what was otherwise a very, very uniform charged plasma of light and matter that was mixing. It was in thermal equilibrium. And what started to happen, the picture is, there were very small microscopic fluctuations in the densities. Some regions were slightly denser than average, other regions slightly underdense. The overdense regions, because they had a bit more mass, started to attract other mass and started to grow, sort of a rich getting richer kind of phenomenon. And eventually those clumps grew and grew, to eventually formed structures that became stars, galaxies, clusters of galaxies, superclusters of clusters, a hierarchy of mass that we see today. So before that formation happened, the universe cooled off, matter and radiation fell out of thermal equilibrium with each other, and the radiation that we now observe as the microwave background, that image I showed you earlier, started streaming freely out to be observed today. And now we see overdensities that in the early universe were essentially microscopic, have grown into subamorphous objects. So that's the picture. So we are looking fundamentally, what I will tell you about tonight is observations on the right-hand side of this diagram, the large-scale structure. It's very complementary to observations of radiation in the universe. But that's too much to govern one talk, so I'm not going to get into it. Okay, so what are the main starting points of modern cosmology from the theoretical side? I have to catch my breath with this mask. Whew. It's hard to talk and breathe in this thing. Okay, so cosmology today rests on two crucial assumptions. Number one, the universe on large scales is governed by forces of gravitation as described by Einstein's theory of general relativity. It has passed every test that's been thrown at it since 1915, and as of now, it's still the best theory of gravity that we have. Number two is the cosmological principle. Now, the way this is usually phrased is something that I already said. Basically, the universe looks the same everywhere. But there's a weak version of this, because the universe is the same everywhere. There's no observable edge. Everywhere you are, on average, got about the same density. I mean, obviously, when you go into smaller scales, it's not uniform, but when you average over a large enough region, everything kind of looks the same. That's the weak version. The stronger version of this, I'll throw a bunch of jargon at you, says the universe is approximated as a stationary and isotropic random process with a power spectrum amplitude and tilt from a model called lambda CDM. And I can show you some plots that illustrate that, realizing that many of those words might not have strong meaning to you. Okay, so I'll throw one equation up here and explain what it means. The consequence of these two principles, these assumptions, is that we can model the universe almost as a kind of fluid, right? That's homogeneous. Okay? It's the same everywhere. It's isotropic. It looks the same every direction you look. Okay, and it lives in expanding space, and it's governed by general relativity. And it even has an equation of motion that explains how it grows over time. Here's the terms of this equation of motion. You describe the size of the universe at any time. You have a term that's called scale factor, lowercase a. It basically tells you how big the universe is. So today the scale factor is 1. In earlier times, the scale factor was less than 1. Okay, and this symbol, A dot, for those of you who remember university physics, that means the rate of change of the scale factor is a function of time. This is sort of a velocity, and this is velocity squared. So velocity squared, if you remember high school or college physics is basically proportional to kinetic energy. So on the left-hand side of this equation, we have something that is like kinetic energy in the universe. And then on the right-hand side, we have stuff that is causing this increase or decrease. And there's 4 terms that I wrote there. One of them is called matter density. It's essentially the matter in the universe, right? That likes to make things, that likes to decrease the expansion of the universe, likes to connect things together. The second thing, I wrote dark energy. That's something I'll get to in the next slide. The third term is radiation. So radiation exerts a pressure, it exerts energy. It can drive the expansion of the universe. And then the last thing is the curvature of space-time. That's actually also a form of energy. So it's essentially potential kinetic energy on this hand, and then potential energy on this side, with different terms computing different things to the potential energy. And that tells us how the universe is going to evolve over time. So the program is, if you measure all of these terms on the right-hand side, you can tell how the universe will evolve into the future. That's part of the program. So the dominant contributions to the energy today come from only 2 pieces. One of them is matter. And when I say matter, I don't mean stuff like this. This is baryonic matter made of atoms. I'm talking about something else. I'm talking about dark matter, which most of you have heard of that. And if you ask me what it is, my answer is we don't know. We have candidates for what we think it is, but we actually don't know what the dark matter really is. And most of the matter, that is stuff with mass that attracts other masses, is dark matter. We actually don't know what most of the universe is. Then the second term there in green, dark energy, that is a kind of negative pressure that seems to be pushing the universe to accelerate faster and faster. Now, what is that dark energy? I've told you pretty much all that we know about it. That's it. It is something that we hypothesize exists in order to explain this accelerating expansion. And there's various potential theoretical candidates for this, but it's really pretty unclear. Okay, so we live in a universe that's dominated by dark matter and dark energy, and we measure that using measures of the expansion of the universe. The model of the universe that's used, there's a quantitative model that explains this. It's usually referred to as lambda CDM. The CDM stands for cold dark matter. The lambda is that green term, dark energy. It's a cosmological constant. It's a term in this equation. It was actually invented by Einstein in the 1920s to try to guarantee that the universe couldn't expand or contract. When Einstein developed general relativity, he realized that his equations allowed the universe to change as a function of time, its size, and he didn't like that. And he put in a fudge factor that basically would keep it static. And this was before Hubble. And then when Hubble made his observation of the expansion of the universe through the recession velocities of galaxies, Einstein said, oh, I made an incredible blunder. But now we brought that term back to explain this dark energy that we can't explain. So it's an interesting history. So this seems kind of an absurd picture, right? Because we have 2 terms that I'm telling you are totally dominating the energy density of the universe: dark matter, that we don't know what it is, and dark energy, that we don't know what it is. And you're probably thinking, okay, this is nuts. And it kind of is, but there's many lines of evidence in support of this picture. Let's see if I can move forward. Seem to be stuck. Move the cursor. The right spot. There we go. Thank you. Great. So I actually have a link to a paper on archive.org by John Peebles that goes through in great detail, probably more than you want, all the different lines of evidence. I threw up 7 of them here. So among the various things that support this view that I showed you, things like galaxy redshift magnitude relation is one. The ages of the stars puts a lower bound on the age of the universe, and that tells us how fast it's expanding, because if it was expanding slower, it would actually have to be older to get to its current size. The abundances of the lightest elements that were formed in the Big Bang. The structures, distribution, evolution of the galaxies and clusters of galaxies. What I'm going to focus on today, measures of the distribution of galaxies in real space and in redshift. and then measures of the cosmic microwave background, which I won't talk about today, but that's been an incredibly rich field of study for since the 1960s. So there's consistency in favor of this dark energy plus cold dark matter model across a huge range of distances and sizes. So here is one plot that just demonstrates this. This is known as the matter power spectrum. And what you are looking at, going from left to right on the plot, is structures from the largest scales, essentially almost the size of the universe, to the smallest scales that are not really affected by very local effects. So essentially from cosmic scales on the left-hand side to galactic scales on the right-hand side. And the data with error bars that you're seeing are coming from a variety of different probes of structure and expansion: the cosmic microwave background, gravitational lensing of the cosmic microwave background, large-scale structure measured through various probes. And then the black line is a fit of lambda CDM. Okay, so without really understanding exactly what you're looking at, you can see the fit's pretty good, right? So it's the most parsimonious model that we can come up with that seems to describe the data across a huge range of size scales with many, many different types of cosmic probes, almost from the earliest types of matter that we can measure, the earliest data that we can measure, the cosmic microwave background on the left-hand side, to galaxies and clusters on the right-hand side. So that's a bit about how we know what we know. In terms of dark energy itself, really what we want to do to characterize it is we want to measure the expansion of the universe. And there's different types of observational techniques for doing this. When you measure the expansion of the universe, part of the trick is that the universe isn't just smoothly expanding. There's also, when you're measuring things like galaxies and clusters, they gravitationally attract each other. So galaxies like to fall towards each other, but then the underlying space is also expanding. So you have to, it kind of confounds the measurement a little bit. So you have to be able to separate these carefully. So that's why we use all these different types of observations. So the quantities that measure the smooth expansion are what I'll call standard candles, which I think is a term you've heard before. Henrietta Leavitt's Cepheid variables were standard candles. Type 1a supernovae are standard candles. Standard rulers, you probably heard of standard candles. I don't know if you've heard of standard rulers. It's a similar concept that measures distance and thus the expansion of the universe. Now that we have gravitational wave measurements, we even have something called standard sirens, which I won't talk about, but if you want any information, just ask me and I'll get into it. And then the cosmic microwave background, which I won't discuss. So that is the big picture. Okay. So how do you actually measure distance and the expansion of the universe? So I showed you Hubble's data at the beginning. This is basically a kind of cartoon version of Hubble's plot. So in the nearby universe, the further out you measure, the higher the redshift of galaxies, the further distance you're measuring. And then you can actually measure a relation that looks like this. This is actually Hubble's law, right? The velocity, the recession velocity of objects as a function is directly proportional to their distance from us. The farther they are, the faster away they're moving. And so in the nearby universe, you get a straight line that looks like this. In the more distant universe, that relation gets a little bit more complicated. You actually get a bit of curvature in this line, and it looks like those terms in the upper right. Without belaboring exactly what they are, you'll see that you may recognize a couple of the symbols that are there. There's this omega sub m and this omega sub lambda that shows up in the right-hand side. Those are dark matter and dark energy densities. So by measuring the expansion of the universe, you're sensitive to these two cases. Okay, so the trick is, how do you measure distance in a nice, convenient way that lets you pull out those terms? That's basically what we're trying to do. So the first way, the classic way, what Henrietta Leavitt did, what Hubble did, what has been done since the 90s with supernovae, is looking at standard candles. So the idea with a standard candle is that it has a nice calibrated amount of light. Its intrinsic brightness is well known. So the assumption is we know what this quantity is, and then you measure a flux in your telescope, and the difference between the light emitted, which is known and fixed, and the measured flux is just this divided by 4 pi times the distance squared. Now, distance gets a little bit complicated in an expanding universe. So I wrote there 1 plus z times something called co-moving distance, because you have to account for the fact the universe is expanding while the light is coming to us from a very, very distant source. But it can still be done. It's basically luminosity divided by 4 pi r squared, right? So the idea is if you know the intrinsic brightness of an object, you can independently get a measurement of the distance to the object just by measuring the flux. And examples of this are Cepheid variables, type 1a supernovae, and other types of things. That's not the only way, though, to get a distance measurement. You can also have things like standard rulers. Excuse me again, I have to catch my breath. Whew, okay, got it. So the way a standard ruler works is imagine that you actually had an object whose size you know, and you put it out there on the sky. So for example, I'm holding here a little stick, like a little pointer, right? If you knew exactly what the length of this was, sitting where you are, you could measure the angular diameter of this from your point of view. And as I move towards you, the apparent angular diameter gets bigger and bigger. So you know that I'm moving closer, right? You're so attuned to doing this your whole life, you don't even really know what's happening, but that's what's happening. So if there were some sort of object in the universe that had a standard size, a standard linear dimension, we could measure its changing angular size as a function of its distance in the universe and get another independent measure of distance. So this is called a standard ruler. And again, the idea is we know this quantity, the linear distance, we measure an apparent angular size, and then that ends up giving us information about the co-moving distance to the object, right? The measure of distance, but with that extra piece that accounts for the expansion of the universe. So is there anything like that? Yes, there is. That's what Desi is trying to do. So there is a standard ruler. And the way the standard ruler works, it's a little bit convoluted, so bear with me for 30 seconds. In the early universe, before the radiation that we now observe as the cosmic microwave background was basically streaming away from matter, the universe was a dense plasma of photons and baryons, essentially bare protons, bare electrons. Hydrogen couldn't form because as soon as it did, a photon would come in and immediately ionize it. Okay, so the universe was this hot plasma. And the photons move at the speed of light. They have a lot of energy. They would basically blow bubbles in the early universe. They would, when you got an overdense region, it would heat up and it would start radiating photons, and those photons would blow up a little bubble inside the plasma. Now I have here, I don't know if you guys like the slow-mo guys. My kids really like this. This is a video of somebody shooting a firearm in a pool. And what happens here is that the gas from the muzzle blows up a bubble, and then the water pressure is going to start to collapse the bubble. Now, when the bubble almost completely collapses, it's going to rebound, okay? And it's going to start expanding again, and then the water pressure is going to collapse it again. It's going to start expanding again and collapse again. So it's an oscillation, right? There's a force from the gas of the muzzle, and then there's a restoring force from the water pressure, and it just oscillates back and forth like that. So in the early universe, the photons played the role of the force that was blowing up the bubble. So what was collapsing the bubble? Well, what would happen is the bubble would expand, it would cool down, it would kind of overshoot its equilibrium position, and then the dense matter at the center of the bubble would start gravitationally attracting this cooled off plasma, and it would start to collapse again. So you had this expansion and collapse, expansion and collapse. So that's called a baryon acoustic oscillation. Okay, it's very analogous to the gunshot and the pressure oscillation in the video. So the cool thing about this is that eventually the universe expanded to the point that it cooled off enough that hydrogen could form, and the photons that were in that plasma were able to just stream away from the matter, not scatter off of it anymore. Those photons became the cosmic microwave background. So what happened to the bubbles? Well, it turns out that the bubbles were still present, baked into the underlying distribution of matter. So if you actually look at galaxies on large scales, that pattern of bubbles where you have a center of high density and then kind of an edge of the bubble is encoded in the distribution of galaxies on large scales. Now, it's a little bit tricky. This is a cartoon picture. If you actually look at galaxies out there, you don't literally see bubbles like this. You have to dig it out through a statistical analysis, but it's there with high significance. And people actually observed it for the first time about 15 years ago. And now we're using it to actually measure distances, because this is a standard ruler. The typical diameter, or excuse me, radius of this bubble is fixed by the what's called the sound horizon, the farthest distance that acoustic waves, sound waves, could move in that primordial plasma before the photons decoupled from the baryons. Okay, so the idea is you look at a huge number of galaxies. So each one of these little dots represents a galaxy that's tracing the underlying distribution of matter. Okay, and you do a statistical analysis of all those galaxies, and you are able to dig out this standard distance, this standard radius, and then you measure it at all different distances throughout the universe, and you're able to measure the cosmic expansion. So it's very complementary to the standard candle approach where you measure supernovae. There's actually not that many supernovae out there, so you get a much higher statistics, much better measurement of the expansion this way. Okay, so that's it for the theory introduction to what we're doing. Now we're going to get into how the measurement works. And here I think you'll be on more comfortable ground. I'm going to risk insulting everyone's intelligence by talking a little bit about how telescopes work. And then you can shake your head at me vigorously if I get something wrong, because you're all very experienced. So there's two ways that we measure large-scale structure in the universe. The first is photometry. This is what you do. So Mark showed a nice picture of Saturn and Jupiter that was taken using this method, right? Basically, you take light from an astronomical source, you put it through some color filter, you record it on CCD, then you co-add those things, you get a nice picture. So most of the beautiful astronomical images that you fell in love with enough to join the Astronomical Society are done using this technique, right? So this is actually a picture from the Dark Energy camera in Chile that I actually personally took. I got to be on shift there in 2017. It was very fun. So the idea is that you can use these kind of images to identify spatial features. You can make new discoveries through this technique. You can rapidly cover broad regions of the sky and look for cataclysmic explosions. So this is how supernovae are discovered, for instance. There's a number of high cadence, high throughput surveys that are coming online professionally that do this, and most amateur astronomy uses this as well. So this is really well suited for discovering new objects. This is not what Desi does, but we do rely on the technique. So in order to run an experiment like Desi, first you have to do a photometric survey of a large patch of the sky and try to identify good target galaxies to use in your survey, because we want to make a 3D census of the universe. So between 2016 and 2019, there was a survey called the Desi Legacy Imaging Survey, which did photometry across 20,000 square degrees of sky, discovered, or rather surveyed 2 billion distinct objects on the celestial sphere, and then picked out 30 million of them for Desi to target. Okay, the URL for this is legacysurvey.org/viewer, and you can actually view the data. It's all public. Don't do it now, listen to me. But when you're done listening to me, go to the website, play around. This is all public. It's available for you to see. Okay, so that's the first and probably most famous use of optical signals in astronomy is photometry. What Desi is using is spectroscopy, and spectroscopy is the measurement of the flux of light from a source after it's been broken into its component wavelengths with some sort of dispersive element. Okay, and the idea behind this is that you observe particular emission and absorption lines in the spectrum that are due to atomic transitions at known wavelengths in the lab on Earth. But those wavelengths then get shifted either longer or shorter depending on the relative motion of the astronomical object. So if it's moving towards us, all those wavelengths get shifted towards the blue end of the spectrum. If it's moving away from us, they all get shifted towards the red end of the spectrum, hence the term redshift, right? So the advantages of getting a spectrum is you get very, very accurate three-dimensional measurements of the position of a galaxy along the line of sight, and the photometry gives us the angle, right? So you get a radius, and then from the sky catalog, you get 2 angles, right? And that gives us a 3D location. So that's number one. The second thing is the spectra are the best way to classify objects. So the way we almost always tell what something is, even with careful measurements of the light curve with photometry, spectra is kind of the gold standard. So that's how that works, okay? And here's an example of the spectrum of a distant quasar, for those of you who've not seen something like this. And if you want to play around, maybe at the end, we can load up legacysurvey.org on this laptop and we can try to find one of these. Okay, so these two techniques are complementary. The way the Desi survey has worked is that for a couple of years, 2 billion potential targets were observed with photometry, because that's the technique that's good at just covering huge amounts of the sky. And then a subset of those were picked out as suitable candidates for getting that 3D census. And that's what we're observing now. So if you go to legacysurvey.org, unfortunately, the spectra are not public yet. They will be starting in April. But you can see objects that are tagged as individual galaxies. And then if you click on one of them, you actually see the spectrum. So this is the flux as a function of wavelength on the horizontal axis. And you see these tall spikes here. These are well-known atomic transition lines. And their locations in observed wavelength tell us how redshifted the galaxy is, and therefore how far away it is, ultimately. That's how it works. Okay, so spectroscopy occurs usually in 2 ways. Some of you have probably done it at some point in your lives. I don't know if everyone's done it. If you've done it, you've probably used what's called a single object spectrograph. So you take your telescope and you direct the light through a slit. So let's say you're looking at one single star. You try to isolate it. You have a collimator that makes sure the light is parallel. You then put it through a disperser. So I drew that as a little prism, but it's usually a diffraction grating. Okay, and then you project the light onto a camera. So the prism or grating breaks the light up into its constituent wavelengths. And then on your detector, which nowadays is usually a CCD, you see images of the slit, but different separated colors, right, from the spectrum of the object. So that's traditional single object spectroscopy. It's kind of painstaking, right? You got to target one object at a time and record the spectrum. Now, you can do that if you want to get a couple hundred objects, but if you want to get 30 million, you have to parallelize it. So how do you do that? Well, instead of putting light through one slit and exposing to one object, you try to expose to many objects at once. And the way that you do that is you take individual fibers, fiber optics, you target individual locations on the sky, you take the light from those fibers, you pipe them down into a spectrograph, and then you expose a CCD to the image. And the CCD image, I kind of drew a cartoon of what it looks like on the right. Essentially, every fiber produces a vertical column of light. So each one of those vertical columns is a unique source. And then the rows in the CCD going from bottom to top correspond to wavelength. So the horizontal axis on the CCD is fiber number, and the vertical axis is the dispersive axis, that is the wavelength. Okay, so you get a bunch of spectra all at once, which is great. That's how you do it. Okay, so this is not a new technique. Desi did not invent this. This was actually developed for the Sloan Digital Sky Survey, which really started in earnest in the early 2000s, although it was first proposed in the 90s. So Sloan was at Apache Point in New Mexico, 2-meter telescope. And the way that they set up these fibers to look at particular targets is they would actually take an aluminum plate, it's about the size of a coffee table, and then this would happen. A human being would plug them in one by one. And you see there's little markers and little regions drawn on there. That's to prevent confusion of the fibers. So they would have to do the bookkeeping very carefully by hand manually. Then they would mount those in the focal plane of the telescope, point to someplace on the sky where the drill holes, and I'll show you again. Whoops. No, it doesn't want to do it again. All right. Well, I hope you enjoyed it. Can't get it back. Let's try one more time. It's kind of fun to watch. Every time I see this, the Betty Hill music runs in my head. So the idea is the pattern of holes that are drilled correspond to a particular field on the sky that you're trying to target, right? So these plates still exist. The people who worked on SDSS, there's a lot of funny pictures online where you can see people have turned them into literal coffee tables or chandeliers or things like that. And if you know who to contact, you can even get one of them. Okay, so that was fine 15 years ago. That was a good technology. But cutting edge cosmology requires pushing the limits and getting more and more statistics every year. So what you're looking at here on this plot is the history of galaxy counts and redshift surveys going back to the first ones in the 1980s. This image over here is one that maybe some of you are familiar with. This is the CFA redshift survey run out of Harvard in the early 1980s, showing very non-uniform structures in the nearby universe. Each one of the points in there is one galaxy. Okay, and that was about 1,000 redshifts taken by hand. Okay, by the early 2000s, redshift surveys started looking like this. You see, it's much more of a kind of web-like Swiss cheese structure that you start to observe in the galaxy distribution. You know, something like 100,000 redshifts to about 1 million in a survey like this. And if you look at the, if you look at the plot of counts of galaxies as a function of time, you see this is a logarithmic scale. There's sort of like a Moore's law growth in the counts. And that's due to the literal Moore's law, the famous Moore's law. It's due to cheap silicon, right? It's due to CCDs. So that's how it worked. So in the 2010s, basically extending the SDSS technique, the largest surveys have now accumulated about 1 million redshifts. So how do you get to 10 million? Right, this is where we are right now. How do you get here? And then, 10 years from now, how do you get even 10 times more than that? Well, the answer is automation. So instead of having a human being plug a bunch of fibers into a set of drilled plates, you have a focal plane where the fibers are attached to little robots, little positioners, and you basically steer your telescope to a point on the sky and then have the positioners automatically reconfigure the fibers. So that's how Desi works. Let's see if I can play this. So here you can actually see the fibers moving in a test of the positioners. This was done at Lawrence Berkeley National Lab in California. Okay, so this is a picture of the finished focal plane. I don't have a nice movie like that, the finished focal plane, but the finished one has 5,000 fibers like this. The SDSS plates had something like 400. Okay, so many more fibers, almost a factor of 10 more, and they can all be moved automatically. So it takes about 3 minutes to steer the telescope, and basically the whole focal plane reconfigures itself at the push of a button. It's actually much harder than that. It took a lot of work to make it work, but that's the idea. And it works. Okay, so now we get to Desi. Desi is the Dark Energy Spectroscopic Instrument. It's located at the Mail 4-meter telescope at Kidd Peak in Arizona, where perhaps some of you have traveled. It is open to the public, and if you drive down there, you can go see it. They have tours every afternoon. So the Mail is this building. It was built in the late 1960s, and inside is this big telescope. So there's a primary mirror inside of the white box that you see there. Then an atmospheric dispersion corrector. Then a focal plane has our 5,000 fibers that are pointed at 5,000 targets in the sky. Then a lamp system to calibrate everything. You have to calibrate the throughput of the instrument carefully. Then a cable run that takes fibers from the focal plane down through the floor into the basement of the building where they are connected to spectrographs. And that's what you see there. So there's a clean room that has 10 thermally controlled spectrographs. Each spectrograph has 3 cameras, and the whole wavelength coverage is 360 to 980 nanometers. So from basically the blue end of the spectrum to the near infrared. And I'll show you some data in a few minutes. So I'm going to go through the pieces of this telescope one by one, and let me know if I need to speed up from going long. So the first light of the male telescope was in 1973. It was a Rishi Krishan design. The telescope is mounted on this big pier inside the building to isolate it from the vibrations outside. It's really windy there. And you don't want the whole telescope moving because somebody slams their car door or slams the entrance door of the building. You can go inside the pier. It's actually impossible to talk because of the echo, but it's kind of cool to go in there. And I think they do let tours go inside. The mirror itself is 4 meters. It's a fused quartz primary. It's a gigantic thermal mass. When you open this thing up at night, if the ambient temperature is cooler than the mirror, you get tons of seeing from turbulence in the mirror as it cools off. So they don't build them like this anymore, for sure. Now they build them with kind of hollow hexagonal cores so that they cool off much faster. But this thing was sitting there. It was available. To build something like this today would be very expensive. So Desi and the Department of Energy went to NSF's optical infrared lab and said, hey, can we take over your focal plane for 5 years? And they said, yeah, sure, for some money. So that was the arrangement. Okay, so that's the primary telescope. The next piece of the telescope, light hits the primary and then goes through an atmospheric dispersion corrector, which some of you may have used these. I'm not sure if all of you do. For those of you who have never used one of these before, the atmosphere causes chromatic dispersion, right? The index of refraction of air differs very slightly as a function of wavelength. So if you're looking at a source at very large air mass, the source's light, like say a distant star, will actually be spread into a column with different colors as a function of angle, okay? So a dispersion corrector is basically 2 prisms that are aligned on the focal axis of the telescope, and you can orient them to cancel out that effect. That's what it is. So you don't want to build your nice, multi-million-dollar fiber telescope and then have the light spread out into big lines that don't lie in on the fibers. So that's why we built this dispersion corrector. Okay, just to give you a sense of the scale of this thing, these are meter scale refractive elements, so bigger than this table, and they need to be polished to a tolerance of something like part per million on the surface. So it took several years to manufacture these. I don't have a nice heroic image of one of the lenses. They are cool looking, but this is the scale of the dispersion corrector itself. So it's sort of the size of a pickup truck, right? And this thing sits at the end of the truss on the telescope and then moves around with it. So here is the integration of the dispersion corrector on the left. And then on the right-hand side, you see there's kind of mechanical arms on that. That's called the hexapod. It's used to move the telescope focal plane in X, Y, and Z. So you can see the size of this thing. It's pretty big. Okay, moving on, we have the focal plane assembly itself. And this is where the science starts happening, because this is the part that is robotically positioned, and then the light is guided down fibers. So here's what the focal plane looks like, kind of in a diagrammatic form. So the focal plane is divided into 10 like sort of pie wedges. These are called actually petals, not pizza slices. Oh, I think of pizza every time I look at this. So this is number 0 up through number 9 over here. So C-style numbering, not Fortran style numbering. Right, and then behind the petals are quite a bit of electronics that are used to power the positioners And there's artificial light sources in there, which I'll explain what those are for in a moment. Okay, so there's 10,000, excuse me, there's 5,000 positioners, 10 petals, so 500 fibers per petal. The focal plane has other instrumentation that we use to help guide the instrument. So at the corners of the petals, if I go back, you might notice there's sort of a blank spot here, 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 same location in every corner. That's for what we call the guide focus array. So there are 5 CCDs located at 5 different petals that are basically, their whole job is to look at guide stars. So those are labeled G here. The idea is they're looking at guide stars, and you can tell exactly where the focal plane is using astrometry, okay, with standard stars. Then there are 5 other CCDs that are labeled F, and those are to help focus in real time the telescope and make small sort of 10 millimeter adjustments every few minutes as the temperature cools off and the truss is thermally shifting a little bit. And the way that those CCDs work is they're very slightly defocused from the focal plane. So instead of getting a nice spot of stars, you actually get like a little donut shape. And if you're slightly out of focus, like if there's a bit of tilt that shouldn't be there, that donut, it becomes asymmetric. And so we have a piece of software that's basically looking for that and then writes an automatic correction. So it can change the focal length of the instrument in real time. Okay, then when you're actually running the instrument and you move to a new location, what happens is the software commands the fibers to point to a particular location on the sky. And then there is a camera at the top of this telescope that takes a picture of the focal plane. So we can actually backlight all the fibers for a few seconds, take an image, and make sure they actually moved where they were supposed to move. Sometimes the positioners get stuck, and you want to know why, and you want a record of it. So every single exposure, when you actually issue the command to move, everything moves. Then it does like a little bit of a cleanup step. Then it takes a picture, and then you verify in software. You don't have a human being doing this for every single exposure, but you verify that the fibers either went where they were supposed to, or if they didn't, they get automatically flagged for later treatment in the data pipeline. So this is called the fiber view camera. It's mounted in the Cassegrain cage behind the prime focus. And this is recording positions of the fibers every single time they get moved. Okay, another piece that you might be interested in knowing, and I'll show you evidence of this in a moment, is there's other sky monitors that are looking at the sky background. So the reason you want to do that is that the sky background is actually very bright compared to many of the objects we're looking at. Remember, we're looking at stuff that's at a redshift of 3 or 4. That's essentially looking at some of the oldest galaxies we can measure, and the light is very faint. So we want to very carefully measure the sky background, make sure it's not changing too much. When the moon is up, that obviously affects the throughput of the telescope. So there's an automatic system that automatically adjusts the exposure time if the sky background gets too high and starts lengthening the exposure time. And if sky background is low, it'll say, hey, I actually have enough signal already. My signal to noise is threshold is achieved. I can cut this exposure short and move on, which is great. And we've actually had a run of really, really good conditions the last month. So there's been a lot of great measurements using this automatic system. Okay, moving on to the cable run. Let me just show you a little diagram of how this looks. So the cables, the fibers themselves are teeny, teeny, tiny. They're a fraction of a millimeter. They actually look like a human hair. They're actually hard to see even when you're looking right at them. And they're packaged inside of a mechanically solid positioner. The whole assembly is about 3 meters long. Then they're all packaged together into a set of a big bundle of fibers to make them mechanically robust. One of them wraps around the declination axis of the telescope, the other one around the polar axis. Then they go down into the basement, into the clean room where spectrographs live. They're split out, and then they're sent in batches of 500 to the 10 different spectrographs. Okay, the spectrographs are really doing sort of the heroic work. That's where we actually get the information about the galaxies that we want. So here is what one spectrograph looks like. It's got 3 different cameras. So I actually have a little bit of animation in here. So as the light comes in and gets split into a red band, excuse me, a blue band, a red band, and a near infrared band. Okay, so there's the near infrared channel. There's the red channel. There's the blue channel. Okay, so this is the schematic. And so there's 3 separate cameras for those 3 pass bands, and then the spectra get merged back together during data processing. The actual photo of one of these things is shown here. And so this is almost 2 meters across and 1.5 meters deep. So for those of you who are not used to thinking in meters, this is pretty big. One of these would fit in the back of a an F-150. So it's non-trivial size. So a clean room was built in the basement of the Mail telescope. So when you go into the basement, you can actually see this. And then shelving was put in, and the spectrographs were set up in 2 stacks, 5 on the bottom, 5 on the top, and are run under these kind of clean conditions to avoid contamination from dust that affect the optics. Okay, I'll show you some data now, some raw data. So if you look at data coming directly out of the spectrograph, it looks like this. So this was I don't remember what night this was, but I was on shift last month, and so I actually grabbed some of the data we took. So if you guys remember when I showed you the cartoon of the multi-object spectrograph, I said the CCD image has these vertical columns of light corresponding to each fiber. This is exactly what you're seeing. You see these vertical lines. Each one of these is from one of the 500 fibers going to this particular camera. This is one of the blue cameras. So the wavelength on this dispersion axis goes from about 360 to 593 nanometers. Okay, and so the pixel rows from left to right correspond to the fiber numbers, or the pixel columns, excuse me. These in this direction corresponds to wavelength, right? So it increases in wavelength as you move up the image. This is a 4096 by 4096 CCD, so 16 megapixels. Okay. Here is the same exact exposure, but the red camera, the R camera. So that covers 560 to 722 nanometers. So if I go back to the B camera, you notice it looks a lot cleaner, right? There's 2 things that are different. First of all, this thing is full of noisy scratch-like stuff. The second thing is that there's these bands of light that are appearing from left to right. Does anybody care to speculate on what these things are? Have you seen these things before? Some of you who've looked at CCDs? Yeah. So these are airglow lines, right? And that's why they're common to all the different fibers. These little scratches, those are cosmic rays. So when the surface of the Earth is continuously bathed in cosmic muons, positrons, electrons, gamma rays from cosmic ray air showers, and when those interact in the CCD, they make a little scratch that looks like this. So these are little particle interactions. These are little particle detectors, and actually there are particle experiments out there that are just built on using CCDs to detect not light, as in your cameras and in your phones, but to detect particles. So that's what those are. Those are all the straight tracks. These are probably muons. The ones that are slightly bent or look like just little dots, those are probably electrons and positrons. Okay, and these are airglow lines. So now if I go to the final camera, the Z camera, you see the airglow lines are really, really bright and intense. And this is all background that has to be subtracted. Okay, this is called the OH forest. This is basically rotational and vibrational molecular transitions of OH in the upper atmosphere. And if you look at it with the naked eye, it looks kind of greenish. Some of you who've been to really good astronomical sites have seen this. So how do we get rid of this horrible background? Well, one thing I didn't tell you is that we have 5,000 fibers, but in every petal, 10% of those fibers are basically held in reserve and are pointed at a location of the sky that doesn't have any target on it. So it's used to measure the sky background across the whole focal plane very carefully, and then we subtract it off as carefully as possible. So the way the software works is it extracts each one of these columns. It tries to mask out each one of these little record scratches from a cosmic particle, and then it uses the sky fibers to subtract off the sky lines, and then you're left with a spectrum. So here's an example of a spectrum. Oh yeah.
In the background, what is the wavelength significant, or is that just a positional error in the image? Is it significant if they're in different wavelength heights on the image?
So are you talking about like kind of like curvature here?
No.
Okay.
The scratches.
No. It's totally random. Yeah.
Totally random.
Yeah, totally random. Yeah, exactly. Yeah, the positions of the skylines are obviously important. You know, that's a function of the the molecular properties of OH.
Yeah.
But these things just show up. So if you do an exposure for 60 seconds, you read out the CCD, and then you do another exposure, you get a whole different set of scratches in totally different locations. Yeah. It's totally random. Okay, so here is, once you've done all that processing, you pull out one of these columns, you subtract all the sky background, you mask out all the cosmic particles, you get something that looks like this. So on the left-hand side is a spectrum from the B camera, in the middle is a spectrum from the R camera, on the far right is a spectrum from the Z camera, and then you can co-add them at the boundaries and get one nice spectrum. And then conveniently, this display labels several of the really prominent emission lines. And that's how this is a really, really well measured spectrum. Usually we don't get nearly this many strong emission lines, but this one is obviously very well measured. We know exactly what those are. Okay, the last 2 minutes, I'll talk about the design of the Desi survey. So this pie chart here is showing you, there's a question, yeah.
What that looks like.
Mm-hmm.
This is a whole galaxy. If you were looking some sideways there, some stars going this way, would that be enough to?
That's an excellent question. So the honest answer is most of the galaxies in Desi are so far away that they're basically point sources, and they're completely contained inside the fiber, modulo missing the wings of the point spread function. For the nearby stuff that has a spatial extent, we just aim it dead on at the center of the galaxy. But you're absolutely right.
Redshift.
Yeah.
Slight redshift change.
Right. So there's the systematic redshift totally dominates, but if you were to measure along, let's say, the major axis of a spiral galaxy, you would be able to measure the rotation. And actually at U of R, we're doing an analysis that's based on exactly that. And I'm happy to talk about that. If you want to know more, I can easily talk about that for an hour. But that's an excellent question. Yes, we can do exactly that. So the systematic redshift is 99% of that velocity. Then you carefully subtract it off, and you are able to measure rotational velocity of galaxies if you want to. Excellent question. Okay, so this pie chart shows the target classes that Desi is after. And again, this is just a cartoon. So the axis of the pie chart is distance. So this is redshift, and then this is corresponding distance in gigaparsecs. I'm not sure how well you guys know parsecs as distance. Most people know light years, so parsecs like 3 light years, something like that. So in the nearby universe, up to of order 1 to 2 gigaparsecs away, we're going to measure 10 million bright galaxies. These are objects that are close enough that we actually can resolve them spatially if we wanted to. Although when you point at a fiber at a large galaxy, you're only collecting the light from a small fraction of it. But to answer that question again, we can point fibers off center and measure radial velocity if we want. And there are some analyses that require that. A little bit further out, there's a set of galaxies called Luminous Red Galaxies that have strong features that we can observe, and I'll show you one of them. Beyond that, there's so-called emission line galaxies, and they have prominent emission lines. You won't be surprised to hear that. And using that, we can measure the redshift effectively. Then looking almost to the edge of what we can see with Desi, we observe quasars. sort of out here. So there's, a little bit less than 1 million quasars. And then between the quasars and us, the intense light from those quasars can actually be absorbed by neutral hydrogen in the universe. And we can use those absorption lines to measure regions that are otherwise not emitting light. So we can actually measure the distribution of neutral gas with those quasars essentially backlighting, almost like a headlamp through a fog. And if there's a little obstruction in the fog, we can see it. It's kind of what's happening here. So combining all of those different traces of matter statistically, that's how we measure the expansion of the universe. If you don't believe me, here's a plot that shows it. So the nearby galaxies, if you look at spectra, there's various ways you can measure how far away they are. Most nearby galaxies have what's called a 4,000 angstrom break, where the shape of the spectrum actually kind of rolls over as you get to shorter and shorter wavelength, higher and higher energy. Basically, the emission cuts off, and you can fit that, and you can measure the redshift. And so we can actually measure the Hubble expansion of the universe in this region using these kinds of galaxies. Going a little bit further out, you want to look at emission line galaxies that have very, very prominent lines like this that covers roughly this amount of region. And using those emission lines directly gives you the redshift and the expansion of the universe. Then even further out, you get the quasars, and then the absorption features that get you even further out. So you can cover this huge, huge range of distances and measure the expansion of the universe that way. Here is a movie that I'll attempt to play that shows one of these features. It's called the OH doublet. It's basically very, very regions of intense star formation are heated up to about 10,000 Kelvin. They ionize and excite oxygen, and you get this transition that's this very distinctive kind of like two-hump spectral line. It's very, very easy for software to find automatically, so that's why we look for it. And this is a kind of like it's not a time lapse, it's a distance lapse of about 3,000 galaxies taken during the commissioning period of Desi, where this was observed at a large variety of redshifts. You can see the redshift axis sort of shifting to the left here as we're going further and further out with additional galaxies. So that's basically how it works. So the idea behind Desi is just measure as many of these things as we can, as fast as we can, and then try to put it together to measure the expansion of the universe. Let's see if I can move forward. Okay, so what's next for Desi? So Desi is going to run for 5 years. It just started. The survey began officially in May of this year after a COVID delay, and we'll run through 2026. And the questions that we hope it addresses is dark energy constant? Does it evolve as a function of time? Do we actually think that we might need to modify our models of gravity at large scales? Is that a better explanation for the data? These are the kind of open questions we're looking at. So it's pretty fun and exciting, right? It might actually give some evidence against general relativity, which would be the first time that's happened. Under good conditions, Desi can record about 80 to 100,000 spectra in a given night. And just to give you a sense of scale, that would have been about a year's worth of data from SDSS. And just 2 nights ago, the instrument set a record. There was a seeing of 0.7 arc seconds in Kitt Peak. And the best we get around here is what, maybe 2.5, something like that. So with that seeing, Desi recorded 140,000 redshifts in one night, which is pretty incredible. So it's doing very well. Is that going to continue? I don't know. It could sort of be like the proverbial 300 hitter who hits 450 in April and May. And I don't know if it's, we'll be hitting 450 in September. But even if we revert to the mean, we'll still be doing very well. This will make our lives easier in the future if the weather turns bad. So multiplex fiber spectroscopy, the technique that Desi uses, is easily scalable. With the technology that we have right now, it would be possible to build another Desi instrument, but have 4 times the number of fibers. We already know how to do that. So there will be more instruments like this 10 years from now. And the one thing that I didn't get to that's super exciting that many of you probably know about is that starting in the next couple of years, there's going to be a huge batch of new surveys that are coming up. The really big one is the Vera Rubin Observatory, and its kind of flagship is the Legacy Survey of Space and Time, LSST, formerly the Large Synoptic Survey Telescope. So that is, within a couple of years, you'll want to invite somebody who is working on that. There are people at R.I.T. working on that, of course. So there's far too much to cover in one talk. That's where I have to end. I want to thank you very much for paying attention, and please ask me whatever you want. Yes.
Yeah, so you have 5,000 fibers. So to get 140K images or spectral light years, that's 5,000 by 104. That's pretty much how long your exposure is for, I don't know.
Yeah. So the exposures. So then there were something like, I think 40 exposures. Nominally, they're supposed to be about 15 minutes plus 5 minutes of overhead to move, reconfigure the focal plane, take a picture with a fiber view camera, et cetera. When the conditions are that good, it actually runs faster than the nominal speed, and it can cut the exposure short and move on really quickly. So that's why having that exposure time calculator is so valuable, because you can take a lot more data. The conditions are great. Yes. There is. I sent Mark a Google Doc link, so
I'll share the link with
yes.
everybody.
Yeah, it's public. Yes.
So there's been a discrepancy about the Hubble constant is measured by nearby galaxies and the microwave background. It's a little bit larger than the statistical errors of each measurement. They've been oscillating back and forth. Does this data say anything about, does that clarify any of that?
Right. So the precursor experiment from Desi is called the Baryon Oscillation Spectroscopic Survey, or BOSS. And those data are all from the nearby universe and are generally consistent with the slightly higher Hubble constant, as opposed to what you get from the CMB. So CMB, you get something like 67 plus or minus, a few percent. And then with type 1a supernova, you get something like 73, 72 plus or minus a few percent. And it's about a 5 sigma discrepancy now, for those of you who know what that means. So so the open question is, what does that mean? Is there a calibration issue somewhere in the distance ladder, which would throw a lot of things into doubt? Is there some issue with the CMB? The CMB people say, our systematics are rock solid, it's no problem. And the distance ladder people say, we've been doing this for a long time, you guys are screwing something up. So it's definitely a bit of an open question as to what's causing it. The other possibility is that the assumptions, the underlying assumptions in the models that are claiming that these two measurements to be the same, some assumption is wrong there, which is exciting to people, because then it says, okay, the model is actually wrong, and there's some physics that we are not accounting for, potentially new physics. My personal point of view is, I take the lazy answer to this, and I say, astronomy is hard, and the systematics you don't know about are the dangerous ones, and the history of astronomy shows that there's all sorts of problems measuring distances when you forget about something, right?
How does that error relate to expansion of the universe? I mean, is it too large to be influenced by that, or?
Oh, so I guess if I can rephrase your question, does the discrepancy between the measurement of Hubble's constant throw things into doubt about the expansion of the universe, like the acceleration of the expansion of the universe? That might be another way of phrasing.
How, if at all, would that difference be related? One's old measuring the Hubble constant from a long time ago on average. One is measuring it recently. If the Hubble constant is actually changing, you would expect it to be different.
Yeah.
How does the differences they're seeing now compare to what they might expect based on a current model for expansion of the universe?
Yeah, that's a good question. I would say, assuming the model is right, there seems to be a difference that you can't explain just in terms of those uncertainties. So then the question is, if you're going to try to break the model to explain that, then what does that do to all the other conclusions that we've made based on that model, including dark energy? And that's an open question. But it could throw a lot of things into now, which depending on your point of view is actually super exciting, right? So might say we have a new discovery that we're waiting for. And that's not the worst thing in the world, honestly. Just again, from my personal perspective, there's a lot of dark energy that doesn't make sense, right? It's problematic theoretically in a lot of ways. And so if we're willing to say, well, maybe it's just wrong, and we are now going to move on to a better model, that wouldn't be the worst thing in the world, in my opinion, right? There's a question in the back.
What impacts do you anticipate from the James Webb Space Telescope on synergy?
Well, there's a lot of synergy. I think that James Webb is gonna make a really detailed infrared map of the universe. It will do a lot more. It's really much more of an imaging telescope, right? Desi has already picked out all of its targets. So Desi is not a discovery instrument the way James Webb can be, and the way a lot of imaging telescopes are. James Webb will have a spectrograph, but it's a complementary technique.
Any other questions?
We muted online, so if people try to ask online, I apologize. I've not heard anything.
You can unmute yourself if you have the question you want to ask. I don't see any questions here.
There was a question about the video of the pool. Who is shooting the gun? I don't know. You have to go to the Slow-Mo Guys webpage.
How many people are online?
Looks like about a dozen. Yeah. Maybe 14.
Yeah. Give me a second.
Yes.
How far can you move each fiber?
14, yes.
Oh gosh. Right. So the fibers themselves are 107 microns in diameter, and each one can cover the better part of a centimeter. That's the patrol radius. Now the thing that makes it super complicated, and I did not have to fix this problem, is that the patrol radii slightly overlap each other. And so you can have a condition where two fibers will actually collide and the motors will trash each other. So, the software was tested super carefully to ensure that never happens. But it's a better part of a centimeter, that patrol radius. So you cover a lot. Yes.
I still don't see how tiny that is. I mean, how much manipulation, how much is the piezo puts it? It seems like to take up all of the room. I still didn't, I couldn't see that picture to see how you physically move all these fibers with their cladding around. I don't see that piezo. Is it in the cladding?
Yeah, it's in the, so there's a cladding, and then there is like a little head that holds the fiber, and then there's a 2-arm motor underneath that you can't really see, that can move in 2 independent axes. That's sort of like one radius. It's sort of like a compound pendulum is kind of what it looks like almost, right? So there's like one arm and then another arm that comes out, and those two can move independently 2 angles, and through that motion you can cover the whole distance. So the fibers themselves, if you're interested in looking this up, they were developed at University of Michigan, and they have a lot of online documentation. There's also proceedings of SPY that talk about all that stuff in detail. So if you really want to dive into the technical details, there's proceedings from 2020, 2018 that go into it quite a bit. And you can send me an email and I can forward you that material too. Yes. And then
I'm just not sure if this matters because we're using that system to like capture so much information. Fiber, is it like tagged so that you can like verify the spectrum that fiber is?
Yeah, so every night there's a whole series of calibrations that are done to check the throughput and to flat field. And we also know from the photometric survey that was done for the Desi targeting, we have a pretty decent idea how much light should be going down every fiber. for almost any kind of observing condition. So if that's really, really different, you know, you can flag that as going wrong. Then if the pipeline itself has trouble fitting the redshift, there's an error flag that says, I can't really tell where this galaxy is, and then it doesn't get used in an analysis. And then, you know, we also have other things like the fiber view camera that if a positioner gets stuck and it doesn't go where it needs to go, then it gets flagged. So there's multiple kind of layers that tell you when something is wrong. Yeah, there's a question here.
Yeah, speakers that I've heard talk about this, you did a great job.
Thank you.
Many people, when they present these theories, have talked about dark energy and dark matter as if they've got a baggie of each in their back pocket and they're not going to share it with anyone. You're the first speaker, I believe, I've heard that has talked about the reliability of the mathematical terms that seem to imply some skepticism about the baggie theory.
Well, the way I would put it is the models of dark energy and dark matter rely on the assumptions that are very reliable assumptions. We have strong reason to believe in them, but they are nonetheless assumptions. And when you follow those assumptions, we get to this theory that fundamentally is pretty weird, right? It's, you know, the universe is mostly made up of stuff we don't understand. And so, you know, it's always healthy to question, is there any way that those assumptions could be wrong, that I could go back and get something that's more reasonable, right? That doesn't require me to invent a bunch of things that we don't understand. So, and the answer for now is still no. The answer is this model is the best model that describes the data, even though it requires us to assume that these things exist. But I think it's healthy to always just not be skeptical, but just always go back and say, well, let me just make sure my assumptions are still right, given what I know now and what I know 10 years from now, right? And the history of science shows that you can sometimes go wrong by not questioning those assumptions. So I think everybody does it. Not everybody who comments to the public is, you know, says that, because, you know, sometimes that kind of conditional conclusion making that we do in science isn't something that's easily transmitted. But you guys are a pretty educated audience, so I think you can handle it. I'm not trying to flatter you, but you know.
Is there another dark energy instrument on the horizon that is in the works?
Yeah, there's quite a few. So measurements of the cosmic ray microwave background will be very sensitive to dark energy. So there's a new plan to build a big facility called CMB-S4, stage 4. That actually, there was just a big decadal survey for astronomy released by NASA yesterday, and they said, yes, CMB-S4, we should build it. So in the next 10 years, that will be built. The Large Synoptic Survey Telescope, which is now the legacy survey of space and time, Vera Rubin Observatory, will also be very sensitive to dark energy. They're not going to measure spectra, but they do have tricks to try to extract distances to objects using just the photometry. It's not as accurate, but when you have tens of billions of targets, you can make up for a lack of accuracy with statistics. You can beat down the uncertainties. So they'll do really, really well. That's going to run for 10 years. It's been delayed by COVID, as has everything, right? Because you have to ship people and material to Chile. But I believe they're supposed to start operating full-time in 2024, and they'll run for 10 years. And a variety of space missions. So ESA is running a mission called Euclid that's almost like Desi in space, I guess is the way to put it. And there will be other spectroscopic surveys out there.
Any other questions?
It's pretty big. In terms of like the core team that built it, I would say it was really run out of Lawrence Berkeley National Lab in California. And there's a team of order 40 people there, most of them full-time staff. And then if you integrate over all the countries that are involved, I think the collaboration is something like 500 scientists. Something like 500 scientists, 30 to 40 universities. Yeah, but Berkeley Lab is the big kind of central facility. Mm-hmm.
How many times a year does this operate every day?
That's a great question. It operates every day, including even full moon. And the only time it's really off is in the summer, because from June to August in Arizona, there's a monsoon season where reliably there's thunderstorms every night. And so basically every astronomical facility in Arizona shuts down for a couple months, which is actually a great time to do repairs.
What's the price tag?
Oh gosh. Maybe I should defer that to the project manager and let them. I mean, it's a multi-$100 million instrument, but I think it's actually fairly cheap given that the facility is a legacy facility that was built in the 60s, and we were just basically able to repurpose it. So it was really a new focal plane and new spectrograph built, but not a new mirror, which would easily turn into $1 billion instrument. So I want to say something that's like $200 million. And of course, a lot of that is personnel, right? Because it takes the better part of a decade to build that, and you got to pay people to do it. So it's not just the material. So all those salaries and things are folded in. That's a ballpark. It might be a little more, but it's it's not $1 billion. It's something like 250 million.
Anything else? Awesome. Thank you so much. I appreciate it. Awesome stuff. Awesome stuff. Well, let me bring Peter Blackwood up, get the results of our election.
Mark, you are no longer president. They wrote me in. Okay.
There you go.
Hi, everybody. I only had 23 people here that gave me ballots.
24.
24. Thank you. That throws all the numbers up.
Yeah, go ahead.
I think, and I'm just speculating on this, that the way this is written, where it says vote for one person for each office, that a couple of people might have confused the fact that there were 3 people written as an office of director. There are 3 directors, basically, so you weren't choosing between those 3. Did it make any difference on the vote tally? No. Out of 24, including this one Mark just handed me, Mark got 24 for president, vice president David Bishop 24, Eric Day treasurer would have got 23, Vicky Rotolo for secretary got 24, Tony Gollenbeck, director, got 22, Bill Rogers, director, 22, and Bill Schlein, director, 23. So everybody's in, and yes, you are continuing to be our president. Thank you.
One more year. Thanks, Peter. Appreciate it. All right, with that, that's it for November's. Oh wait, Jackie, I do have an envelope with something in it. I have tickets for a presentation of Blackfriars Silent Sky, and I'm going to write down a number on the back of this ballot. Between 1 and 100. Now, how am I going to make sure that everybody gives me a number? Let's go across. We'll go across the room, and everybody online, you could type in a number. Give me a number.
25.
5. Sure.
89.
Give me a number between 1 and 100, Ken.
24.
Peter?
I'm going to be out of town.
Okay.
Well, 77.
That's it. 77. That's what I wrote down. Yes. I did not think it would nail it right away, but Dave Thompson won the tickets for Silent Sky. I have them in my, make sure you see me on the way out. So excellent. Excellent. Thank you, Jackie. I would have forgotten about it. All right. That's it for tonight's presentation. Look forward to seeing everybody in December at the planetarium. We have a lot of stuff going on for that. Barring that, we got open houses, and we have member observing. I know there's some people that they're interested in going to Applebee's, so if you're interested in having something to drink or a snack, Applebee's afterwards over at West Henrietta Road. Thanks, everybody. Have a good night.
know, and I've looked at them so many times.
Good night, everybody online. Good to see you guys.
Night, good meeting. Congratulations on being reelected.
Thank you.
Thanks a lot.
No, no, no.
All right, I figure out how to get my cursor over here and close this off. All right. Thanks, everybody.
I'll see you, Mark. Thank you very much for everything.
Thanks, Bob.
Mark, thank you very much.
Thank
Good
you.
night.
Pleasure.
That was awesome. Thank you.